a container or a receptacle, something, a container. Here's a container, plastic paper cup. I need water in it, and then I need heat to raise the temperature of the water from whatever it is today, right now. If I go to the tap, the cold water tap, and I open it up and I measure the temperature, whatever it is, 7, 9, 12, 15 degrees Celsius, whatever it is today, we say that today's water temperature, we call that ambient temperature. Ambient means whatever the water temperature is today. Can be anything. But we know this, that we've got to raise the temperature of the water. In other words, heat, fire, an electrical element. And we're going to heat the water up, and heat it and heat it and heat it and heat it, and raise the temperature up to a certain temperature where the water will change from a liquid, water, into a gas, steam. And there is a specific temperature that is required to be reached. And that water boils at approximately 100 degrees Celsius. Degrees Celsius, or degrees C as it's commonly known, is only a unit of measurement. It measures temperature. I get other ways that I can remember, I can measure temperature. I can measure temperature in degrees Fahrenheit, which is more an American or an imperial system. I can measure temperature in kilowatt, in kilojoules, in kilocalories. Those are all different units that are talking to temperature. The one that's most common, that one that we know and that is most commonly used, is degrees Celsius. For example, what is the temperature today? This morning's temperature when I left home was at 7 degrees Celsius. It is probably now going to be in the region of 21, 22, 23 degrees Celsius. My body temperature is 30, what is it, 32, was it? I don't even know what.
46.
36, eh?
46.
46. No, I think at 46 you're dead.
46, 36, something like that. Might be wrong.
Well, human body temperature, I used to know it. Fucking hell, get a blank. Never mind. So, degrees Celsius is a unit of measurement. So what are we trying to do? If water boils, and I'm right in that, approximately at this altitude, water will boil once I raise the temperature, heated it more and more and more, and when it reaches 100 degrees Celsius, something very interesting happens. That inside the water, tiny little bubbles of steam appear. And these little bubbles in the water are lighter than water, so what happens is these bubbles will lift up to the top. And when it reaches the water's surface, it releases steam into the air. Now, we've all seen it happen 1,000,000 times. Even if we are not boiler operators, we have witnessed that millions of times. How? A kettle. A kettle is a typical example. There's one right here. At this temperature, if I raise it and I turn the electrical element up, it will heat this water and continue heating it until the temperature of this water reaches 100 degrees Celsius. And once it does that, the water will start to boil. And it will release those steam bubbles in the water, and it will come up to the surface. And then if I open it up, and there's not even water vapor at the moment, but normally we would have seen a little bit of vapor coming off. That is now steam. I've changed it by heating it up to 100 degrees Celsius, and I'm changing it from water into steam. But steam then is water, isn't it? It's just water in a gas form, which we call steam. So we all know what happens. When we fill the kettle up, and we put water into the kettle at a certain height, and then we switch on the electrical element, electricity now flows through this element, and as it flows through this element, it transfers the heat from the element into the water and causes that water to raise temperature till it reaches 100. Eventually, it will release steam. Now, if that steam goes out of the spout of the kettle and goes away into this room, for example, what's going to happen to my water level? It's going down. Because the water has left. Therefore, the water that remains behind, even though it's in the form of steam, the water level is going to drop. So, and we also know certain things happen here in my element. It's the heat that I need to convert it to. So let's cut a piece of this element and turn it around, and I'll show you what it looks like. That's what it looks like. So let's look at what we've got here. First of all, we've got a metal pipe with probably about 1 to 1.5 millimeter wall thickness. You guys are with me when I talk about wall thickness? That means the inside measurement of the pipe, of the element, come, Eva. The inside measurement to the inside measurement. So I've got an ID, and I've got a measurement from the outside to the outside, and if I subtract the inside from the outside, I will then be able to work out in how many millimeters in this case is the thickness of this pipe. For the sake of this discussion, we'll call it a wall thickness of, let's say, 2 millimeters. Should we do that? Okay, so the wall thickness of this element is 2 millimeters. Really tiny, really thin pipe, right? And inside this pipe, what have we got? Well, first of all, we've got an electrical coil. What does that do? When I apply electricity and electricity flows through this coil becomes incredibly hot. You can't touch it, it'll burn you to pieces, and it is incredibly hot. It builds up an enormous temperature. This magnesium oxide powder, this white powder here, just ignore that. The only reason why that powder is there in an electrical element is so that we can keep the coil, that electric coil, so that we can keep it in the middle roughly. We don't want it to lie on the bottom of it. We want to keep it in the middle. That magnesium oxide powder does absolutely nothing for us here. So, inside the ID of the pipe is a coil which, when we put electricity, gets enormously hot. What happens to that heat? It flows along that element coil, doesn't it? And then it returns out, and then it flows through the coil. So the electricity continues to flow through this coil, which is making this coil remain at a very high temperature. Do we agree with that? That makes sense, right? Cool. Now what happens is, what is on the outside of this element when it's working? What surrounds this element in my kettle? What surrounds this element? Water.
H2O.
Water, H2O. It's water. The kettle, we know that from experience that we must never let a kettle run with electricity in the coil heating it up without water, because otherwise that element is going to melt and short circuit, yes? We do know that. Cool. So when we boil water, we always make sure that we have got enough water in it so that we can protect the element. So what happens to this heat? This heat transfers. The heat pushes out all the way around, pushes out, goes through the wall thickness. The heat pushes out and into the water that surrounds it. Now, the temperature of this water is, while the coil element is on, that water is going to raise in temperature. And if this is the bottom of the kettle and that's the top of the kettle, in the water, little bubbles will form, and these bubbles will travel up and then release off the top of the water as steam into the atmosphere. Does that make sense? So what are we doing? We're transferring heat into water, raising it from ambient to 100 degrees Celsius, so that steam bubbles can form in the water, come to the level, release, and that's the steam that I want to use. You see, your factory has boilers, but you don't need boilers. You're going to say to me, yes, we do need boilers. I'm saying, no, you don't need a boiler in your factory. What you need is temperature. You need heat. Now, there are different ways of making heat. I could use electricity. in coils or elements or heaters. Like this room is cold, I can put an electric heater here and I can make that electricity goes through, the heat can warm up the room. I need heat in this room, just like you need heat in the machines in your factory. You need heat. You are using steam as a means of heat. I'm using electricity to give me heat. I can use wood, and we can make a fire in this room. And we can light the wood and we can burn it, and it can make heat, and the heat is now going into the room. I could have this coal or wood burning underneath the machine to make it hot, but I'm going to set the place alight. It's not really worth it, is it? I can use steam. I can take a boiler, put it over here, I can heat it up with coal or whatever, and I could create steam inside here, and then take the steam, when it is boiled and it's in my boiler, at the top of my boiler, I can open up the main steam valve, and that steam now, not like a kettle going out of the kettle going to atmosphere, I'm not using that heat at home. I want the water to boil so I can make myself a cup of tea or a cup of coffee. When you need heat in the factory, you need the steam, not the water, but you need the water to make the steam. So we're using steam as a method, a means to carry the heat and take it to the factory. Now, I need to put electricity to my projector this morning. I need electricity there, but the electricity is not over there. The electricity is over there. So how do I get the electricity from there to there? I put an extension lead. The electricity is available there, and I put the electricity in an extension lead, and so I can use it over here. The heat that a boiler makes gets made in the boiler, and my extension lead to bring it to the factory are the steam pipe, the main steam line. So the main steam line is working like an extension lead, isn't it? I can't allow the steam to leave the pipe, because then all the electricity to leave it here, then it's not going there. I'm not going to get the benefit of the heat or the electricity if I've got a broken or an extension line that's going off the other direction. So, we don't need steam because of steam. We are using steam to carry the heat from where we make it in the boiler to inside the factory. Once we've got that idea, once we understand fully what we're trying to do with the steam, we start understanding that the factory does not want kilograms of steam per hour. My boiler size is kilograms of steam per hour. I don't need kilograms of steam per hour, I need heat. And this is where the interesting thing comes in, which we're going to learn about now. First of all, you get different types of boilers. So let's start off with a type of boiler. We've got a vertical boiler. A boiler that's vertical. Your boiler is not vertical, it's not standing up straight, it's standing horizontal. Why is it horizontal? Because it's a smaller boiler, smaller capacity, smaller kilogram of steam per hour. Remember, the size of the boiler is determined by how many kilograms of steam per hour it can make. Your boiler is 15,000 kilograms of steam. Right, that's the one part of it. So how do we make this kilograms of steam? It's in a horizontal boiler, and let's look at the design of it. I have a big pipe, and I put a stoker inside here. What is a stoker? A stoker is a piece of equipment that allows me to use coal as a means of fuel. So it's a piece of equipment that will take the coal, put it on a grate, it will burn, it will light, and it will give off a lot of heat. And that heat is like my electrical element, isn't it? Because what am I trying to do with that heat? I'm trying to put that heat into the water that's inside my boiler. By doing so, I'm going to raise the temperature from whatever ambient it is today, and I'm going to raise it to 100, and once the water reaches 100 degrees Celsius, steam bubbles are going to release, and then the steam is going to be captured in what we call the steam space, which is in the top of a boiler. Why? It's because steam in bubbles is lighter than water, and it will want to float to the top. Steam rises, it doesn't drop down. So I've got a big pipe, I've got this big stoker on there, so that it makes fire. Now, I can make fire with diesel, a diesel burner, a paraffin burner, or an LPG gas burner, and make a big flame inside my boiler. It's very simple. This boiler, for an example, doesn't have a stoker. It's got a burner that uses a diesel or paraffin liquid to burn. Makes a big flame. But we can still use the design to understand, we'll get to the coal side later. But now, just for us to understand how this operates, is I create a huge fire inside here. And I need to make a big fire. To make a big fire, I need a big pipe. I can't make a huge fire in a small pipe. So I need a big pipe to make it in. Why? Because fuel requires oxygen to be present for it to be able to burn. So if I put a lot of fuel inside the pipe, I've got to add a lot of air into it, so that the air can mix with the fuel, and then when I light it, it'll make up a flame. A flame without air cannot burn. So that's why my first pipe, or we can call it my first pass, here comes the shit in English, guys. Sorry guys, that this course is in English.